Alright, so today's lesson, or this lesson, is still in 1.3, but now we're looking at domains, alright? So I'm going to do a bunch of different examples of solving domains. Again, domain is something you should have seen before. This hopefully is just a good review of domains for you. Alright, so domains, we're going to hit domains first, and then we'll talk about ranges later on. We're going to come at ranges more in terms of graphical. So we'll kind of come back to ranges in a little bit. We're going to focus on domains since those are the harder of the two. So a function is defined by an equation. So if a function is defined by equation and the domain is not indicated. So if we're doing an application problem and it doesn't indicate that it's positive real numbers, or I can only, have up to 1,000 people. All right, that would be a given domain. If it's not given to you, the rule of thumb is to assume the domain is the set of all real numbers that replace the independent, basically all real numbers that can go in as the independent variable. And they have to produce real number dependent variables. Alright, so it's all real numbers, no imaginary numbers. And that's part of our check when we're going through and finding domain. Alright, the range then is the set of all independent values that correspond to those domain values, which again, we're going to focus more on the range in a little bit when we get to graphs. We're going to do ranges graphically. Right now, we're going to do the domains of functions given an equation, and then we'll get to graphs, and when we get to graphs, we'll look at domain and range graphically. Alright, so when you're looking for the domain of a function given an equation, alright, start with the domain as the set of real numbers. So again, first we're going to start with, alright, so right now all real numbers are at play. Alright, that's basically what that statement is saying. All real numbers are at play. Then if the equation has a denominator, alright, division, you exclude any numbers that cause division by 0. Right? I can't have, if you get out your calculator and you try to take 2 divided by 0, it gives you errors. You can't divide by 0. Alright, so that's the first check. If I have division, I can't have division by 0. Then I need real numbers, right? In order to be in the domain, it's got to be a real number, and I have to get out real numbers. And so that's the second check. Well, what can cause me not to have a real number? Well, if we have a radical means root, square root, cube root, fourth root, sixth root, whatever, it's a root. So if I have a radical in my equation, a root, you have to exclude any numbers that cause the expression inside to be negative. All right, those would give me an imaginary numbers, and I don't want imaginary numbers. Okay, and so when we give the domains, either use set builder notation or interval notation, and a lot of times we actually want interval notation. Now when I go through the examples, I give you both. Interval notation and set notation is something we assume is a prereq skill. The book does review it, so in case you want to review if you're a little bit, and I will go through it as we do examples, so I'll kind of state it out for you. But if you want to review it, in your book on page 36, that's true even for the ebook, it's on page 36, it reviews the set builder notation and the interval notation for domains. Alright, so now we're just going to practice finding some. Alright, so kind of look at different cases. Alright, so the first one is our function f of x is equal to 5x squared plus 2. So again, first thing we assume all real numbers. And then we have two checks, right? Alright, so start with the set of real numbers. Is there a denominator? Nope, no denominator. Is there a root, right? A radical? Nope, there's no root. And so there's no problems. And so that means the answer is all real numbers. Alright, are all reals. The interval notation for that is everything between negative infinity and positive infinity. That's the interval notation for all real numbers. Alright, everything between infinity and negative, and you would put parentheses, not brackets, because can't ever get to infinity, can never get to negative infinity. Alright, and so either one of those are fine. This is just the description, the set description, all real numbers. And then this is the interval notation. Real numbers mean everything between infinity and negative infinity. Alright, next example. Alright, example B, which is g of x. So g of x is equal to 3 divided by x squared minus 4. And so again, first I start with real numbers, but then I look at and I have case 1. Right? I have a denominator. I have division. I can't divide by 0. So that's the first statement. I want all real numbers of x such that x squared minus 4 cannot be 0. I have to exclude those. So that's sort of the verbal description of what I'm going to solve for. So I have to throw away, exclude, any of those guys that cause the denominator, right? The x squared minus 4 is in the denominator, to be 0. So that's what I have to figure out. Well, I solved this. So I solved this. So first thing is add 4 to the other side. So I get x squared equals 4. Take the square root. Remember, the square root property is plus or minus, right? The square root of 4 plus or minus, because the square could have gotten rid of a negative. So I don't know if that x value was a negative or the x value was a positive. And so don't forget, whenever you use the square root property, plus or minus. And so there are two answers. Right? X equals the positive square root of 4, and x equals the negative square root of 4. And then you simplify that. Square root of 4 is 2, and negative 2. Alright, so what we don't want, if I throw 2 in here, I'm going to get, and you can check it out. If I throw 2 in, 2 squared is 4, 4 minus 4 gives me out 0. Same thing with negative 2. Negative 2 squared is 4, 4 minus 4 is 0. And so these are the numbers I don't want. And so when we want to go to our domain, there's two ways to write it. Alright, so first the set notation. The domain is the set, all x such that x cannot equal 2 or negative 2. Right? That's what that means. It basically is that word. X can be anything with the exception of 2 and negative 2. The interval notation, again, remember, interval starts with infinity to negative infinity. So I'm going to go to infinity and go to negative infinity. But then I break where I don't exist. And so the first break would be at negative 2. So negative infinity, negative 2, it breaks, it doesn't exist. And we use or. Between the 2's, I'm fine, right? I can pick 1, 0, and those are okay. Right? But then my next break is at positive 2, right? I break at 2 and I break at positive 2. And so then I go 2 to infinity. Right? And there is my interval notation. All right, so both of those are correct answers. One of them's set notation, one of them's interval notation. All right, next example. H of x equals 3 divided by x. So it's very similar to the last one with one difference. I have plus 4 instead of minus 4. But it makes a big difference. Now, I still start out with the same thing. All right, I still have to check. I can't have division by 0, so I want all real numbers of x. Of x such that x squared plus 4 cannot equal 0. And so I see if I can solve this. Well, I do the same thing. I move the 4 to the other side, so I subtract it. So x squared equals negative 4. Take the square root. But then when I get to this step, the square root of negative 4 is not real. All right, which means that's not a solution. And so what that basically is telling me, and you can kind of look at it and figure this out without solving. You could probably do that without solving, but this would be the proper way to do it. Is there's no number I can plug in to give me out negative 4. Unless it's imaginary, and I don't want imaginary, I can only deal with real number values. And so, I can't plug anything into the x to get a negative out, because every time I square it, it comes out positive. And so all numbers work. And so in this case, there's no problem. Alright, so the answer is all reals are fine. All real numbers is the domain. Which means interval notation, everything between, I can plug anything I want into that between infinity and negative infinity, and it works. I'm not going to have any problems. All right, everything works. All right, so those were a couple examples with divisors. And now we're going to look at a couple examples with roots. All right, so the first one with a root is m of x is equal to the square root of 2 minus x. So remember, square roots, as the last example show, I can't have negatives under the root. And so we want to find all real numbers of x such that 2 minus x is greater than or equal to 0. Positive, it can be 0. I can take the square root of 0. You can plug it in the calculator. Take the square root of 0. Fine. Alright, so I can be equal to 0, but now I've got to be equal to 0 and then positive, bigger than 0. Right? And so this is what I have to solve. And so first thing is move the 2 to the other side. So I'm going to be left with negative x greater than or equal to negative 2. Divide by negative 1. Make sure you remember when I divide by a negative or multiply by a negative, I have to flip the sign. And so it's x, flip the sign, less than or equal to negative 2 divided by negative 1 comes out positive 2. And check it out. If you're ever unsure about these, plug something in. If I plug 2 in, I get 0, and 0 is fine. Square root of 0 is 0. If I plug something in smaller than 2, like 1. If I plug 1 in, I'm going to get 2 minus 1, which is 1. I can find the square root of 1. But if I plug something bigger than 2 in, so if you forget to flip it here, and you check your answer and you plug in something like 5, if I plug 5 in, it's going to be 2 minus 5, which is a negative 3, which is imaginary. So, I know I did it wrong. I forgot to flip my sign. And so this is basically the answer. The set notation is I want the set values of x such that x is less than or equal to 2. All right, that's the set notation. The interval notation is, well, again, we started out with all real numbers, infinity and negative infinity. I threw out anybody bigger than 2. I only want those less than 2. So I know I threw out the infinity side. I'm going to keep the negative infinity side. And so we're going from negative infinity up to 2, and I have equal to 2, which means I included brackets instead of parentheses. Bracket means 2 is included. Parentheses would mean 2 is not included. And so my domain is every number between 2 and negative infinity, including 2. My next example. My next example is very similar, except now I'm combining two things. I've got division and a root. And it's actually the same root we had before. But there are two parts to this, or two ways to think about this. I have the division rule and the root rule. So we want all real values of x such that 2 minus x cannot be 0, and 2 minus x has to be greater than 0, right, positive. And so really this last one incorporates both things. This includes the not 0 to case. So what happens is basically the previous case, except for throwing off the equal to. I now can't be equal to 0 because of the division. And so I have to throw off. I can't include the equal to 0, because if I did, I would have division by 0. If I tried to plug in 2, I would get 2 minus 2, which is 0. Square root of 0 is still 0, but that's in the denominator, so I get an error. And so this is what we solve. All right, we solve basically the exact same thing up here, except we drop the equal to sign. And so, same thing, move the 2 to the other side, negative x greater than, strictly greater than, negative 2 divided by my negative 1. Remember to flip my sign. So x is less than 2, strictly less than 2, no equal involved. And so the answer for my domain is the set notation is the set every x such that x is less than 2. I put negative 2. It should have been 2, right? Negative 2 divided by negative. Negatives cancel. So make sure you change that. I had that wrong. It should have been 2, not negative 2. And there's my set notation. It's the set where every x works that's less than 2, or the interval notation, which is similar to the last one. I go negative infinity up to 2, but this time I put parentheses, right? Here the 2 was included, so it was brackets. Here the 2 is not included, parentheses, right? I can't plug 2 in, otherwise I get division by 0. But everything else works. Everything else from the previous answer works. I just can't plug 2 in, so I put parentheses instead of a bracket. Alright, the last example. There's also two parts to this last example. This last one's probably the more complicated of all of them. And you really have to think about it two ways. There's two parts to it. Alright, so I want all real numbers of x such that, alright, two things have to be true. The denominator can't be 0, so the 2 minus the square root of x can't be 0. And because of the square root of x has to be positive, right? can't have negative values in the square. I can have 0. 0 is fine. Square root of 0 is 0. And I can plug 0 in because 2 minus 0 is still positive, right? It's still a number that I can divide by. And so those are the two parts. Because of the root, I can only plug positive numbers in, right? Because of that root. So that's one part. And then the second part is the fraction part. The 2 minus the square root of x is all, we're dividing by that expression. That division can't be 0. And so this one has to be solved. Alright, this one takes a little more work. I'll probably move the square root over to the other side, so I'm going to add the square root of x to both sides. And so I get 2 equals the square root of x. Get rid of the root by squaring, and I square both sides. 4 equals x. And so I can't plug 4 in and check it. If I take 4 and I plug it into my answer up here, it would be the square root of 4. Well, 2 minus the square root of 4 comes out 2 minus 2, which is 0. And so I can't have that. That causes division by 0. Alright, so what's the answer then? Well, I have to have, there are two parts to it. I have to have all the numbers greater than 0, which 4 is, but then I also have to throw 4 out. Alright, so my domain, using the set notation, it's the set where every x, I can have every real number of x, such that x is greater than or equal to 0, and x cannot equal 4. Alright, both of those have to be true. Positive and 0, and not equal to 4. Interval notation, well, positive means I'm shooting off to infinity. I can't include the negatives, right? So I'm going off to positive infinity. I start at 0. But then I've got to remember there's a break at 4. It doesn't exist at 4. Alright, so I start at 0, and 0 is included, so it's brackets. But I don't go forever. There's a break at 4. So I go from 0, 4, there's a break. 4 is not included, so I put parentheses. There's a break, so I break it at 4. Parentheses, because that's where my break is, and it doesn't exist. And then after 4, everything's fine, right? Everything after 4 is shooting off to infinity. And there would be my set notation and my interval notation for this particular problem. The domain is 0 to 4, break at 4, and then 4 to infinity. Right? And that's the answer. And again, that was a tough one because there were two parts to it that you had to pay attention to. It had both the root problem and the division problem, and you had to look at them separately, right? And then figure out what your answer is from there. All right, we'll stop that. The next one we'll be looking at how to represent functions graphically, kind of looking at graphically in numerical tables. All right, so we'll stop there.